Morning, everybody. How are we doing today? You having a good fall break? Any big events over the fall break? Any big news happen? You got a what? Awesome job. That's good. Anything else? What? You what? Oh, cool. How was that? Weird. I've never been to that one. We went camping. We had a good time. I'll send y'all a picture of that on our camp trip. We are having an exam on Wednesday. Yeah. No.
Yeah, Happy New Year.
Yeah, that's good news. Happy New Year. We will have an exam. It'll cover, the end part of Chapter 3 and Chapter 4. Projectile motion from Chapter 3. But of course, the vectors, we're going to use that until the end of the year. So today I want to wrap up. Oh, I'm sorry. We will have a help session. I'll send you an email out. It'll be Tuesday at noon. And it'll be in Beauregard 210. That's one of these rooms upstairs. I'm not sure if it's this one or that one. But Beauregard 210. Okay? Tomorrow at noon. I'll record it. Last time I had a technical problem, but I'll try to record it and put it on YouTube for you. Today I want to wrap up on these inclined plane problems, and we'll work through a few examples from some of the old exams. You will have several problems that will involve 2D forces, so you need to make sure that you're up on that. And if you look at every exam, there are problems on all those that have to do with inclined planes. So make sure that you're up on that. It's one of the more difficult topics, but we'll wrap it up today. I'll show you what to do. All right? Let's look at this, and I'll just sort of summarize our procedure. This is an inclined plane. We have some forces that are always there. We have two forces that are always there on an inclined plane. We have the force weight, and we have the force normal. Remember, the normal force is always perpendicular to the surface. It will always have a 90-degree angle to the surface. It is not always up or down. So in this case, since the surface is angled, we have an inclined plane. The normal force is not vertical, but it is perpendicular to the surface. The weight, on the other hand, is always directed down because it's always towards the center of the Earth, and the center of the Earth is always down. So that force will always be straight down. Notice that we describe our angle for our incline in this way, but I usually tell students to think of this angle as 90 minus that angle. So for example, if this angle is, 35 degrees, then we would say that this angle is 65 degrees. 90 minus 35, 55 degrees. Okay? So you take the difference in that. If you see different books, sometimes they do that differently, but I find that it's a little easier to keep your x and your y components straight, because then your x component is still cosine and your y component is still sine. But if you switch your angles around, that's not the case. What happens to the frictional force here? Oh, also the frictional force. Let me address this. This is our static frictional force, Fs. What is the direction of our frictional force? In this case, it's up the inclined plane. But in general, what is the direction of our frictional force? The frictional force always does what? Okay, very good. Always. It opposes the direction of motion. And so in this case, R, it opposes the direction that the object would tend to move. So in this case, the block would tend to move down the inclined plane, so the frictional force is up the inclined plane. However, if I was pushing this block up the inclined plane, then the frictional force would be opposite that motion, or down the inclined plane. The frictional force always opposes the direction of motion. How is the frictional force affected if the angle theta is increased? Well, let's draw our free body diagram. There's my x and my y axis. That's the same as what I had over here. Notice that I've rotated it back. And then I'm going to draw all my forces that I have. I have my normal force here, my static frictional force here, Fs, and then the other force, the only other force that I have is the weight, But I'm going to go and resolve it into its components, into its x and y components. So this will be FWX, that is FW cosine of 90 minus theta, whatever theta is. On your problems on the test, you'll have some number, so you'll just put in that number. And then over here, I have FWY equal to FW sine of 90 minus theta. All right? So what is going to happen if I increase this angle theta? What is going to happen to my static frictional force if I increase the angle theta? Well, there are a couple of things that are going to be at play here, because one of the things is going to make the static frictional force increase, and one of them is going to make the static frictional force to decrease. It's kind of a nuanced thing, but we'll sort of look at both of them. In one hand, the static frictional force will increase. Remember how we talked about if I push this with 10 newtons, the static frictional force is 10 newtons. If I push it with 15 newtons, the static frictional force is 15 newtons. In a similar way here, as I have my inclined plane and it goes up, 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 the static frictional force will need to increase in order to hold it in place. So the static frictional force increases because FWX increases. Because as long as this thing is not moving, Fs will equal FWX. And if FWX increases, then Fs is also going to increase. But on the other hand, Fs will decrease. Or really, Fs max, we'll call it, the maximum static frictional force will decrease. Remember, my static frictional force is less than or equal to mu s times my normal force. And I'm saying that it will decrease because one of these quantities, either the coefficient, mu, or the normal force will decrease as the angle theta increases. Which is it? Is it the coefficient of static friction will decrease? Or is it that the normal force will decrease? The normal force will decrease. The coefficient is always the same. The coefficient is dependent upon the surfaces. And as long as the surfaces are the same, then the coefficient will be the same. But here, my normal force will decrease. And since that decreases, the static friction, the maximum static friction will decrease. If you think about this, my normal force here, if I have an object sitting on a horizontal surface, the normal force is equal to everybody thinks it in their head, on a horizontal surface, the normal force, what the heck is he talking about? Normal force? I don't remember normal force. What is he talking about? What is the normal force equal to if I'm on a horizontal surface? The weight. On a horizontal surface, the normal force is equal to the weight. We've seen that before because those forces are equal and opposite. But as I have an incline move up, what happens to the normal force? It decreases. And imagine as I go all the way to a vertical, what is my normal force then? What is the force that the surface is pushing onto that object? It's zero, right? It doesn't really make sense to even think about a normal force because the surface doesn't push on it when it's in a vertical situation. Okay, so a couple of different things happen there. Now let's work through a problem, and then we'll do a few from the old test just to give you some flavor for what you're looking for. There are couple homework problems for you to do as well. These are the basic steps, and these steps you'll do every time you see a force problem. You'll choose your coordinate system. It's going to be fairly straightforward to choose your coordinate system. In fact, with the inclined plane, we'll always use the same coordinate system. We'll draw the vector diagrams, and we'll also resolve all the vectors onto their x and y axes, and then we'll apply Newton's second law. And then from there, it's just solving the equations. So choose the coordinate system. Our coordinate system, the x-axis is in that direction. The y-axis is in that direction. Making sure that we realize this is plus x, this is minus x, this is plus y, this is minus y. We need to think about our angles, or let's label all of our forces. In this case, this object is not moving. Right? This is an object that's just sitting on the inclined plane. It's not moving. And I have a static frictional force, Fs. This is Fs. I also have the normal force here, and then I have the weight. These are the only forces that are acting upon it. Remember, your normal force and your weight will always act on an inclined plane. Your Fs may not. Yeah, China? I just gave it to you. I wrote it on there. The angle theta is 40. Okay? I'll always use that for your inclined plane problems. Okay, so I want to know, did I ask something here? Oh, what is the minimum mu, the coefficient of static friction, so that this thing doesn't move? What is mu s equal to? But before I even start to think about how I'm going to solve for mu s, I'm going to draw my vector diagrams. Let's first draw a vector diagram and resolve all the, I'm not going to skip that step. So I'm just going to redraw all the forces here. I have my normal force, I have my static frictional force, and then I have my force weight. And this angle is 40 degrees, right? Is that right? Is it right? Right, it's 50 degrees. So don't fall into that. Make sure that you're very careful with that you get the right angle. I got this angle 50 because this is 40. Remind you there's a triangle here. You can probably see it. I'll outline it. If this angle is 40, this angle has to be 50 degrees. All right, that angle is 50 degrees. That's FW. I'm going to go ahead and put in my value for FW. It's a 10 kilogram block, so that means that my weight is it's 100. That's right. I say 10 kilograms times 10 meters per second squared, and that's equal to 100 newtons. So that's my FW. Now I'm going to resolve my vectors. You could do this on the same diagram if you want, but I'm going to do it separately. Here I have Fn, Fs. Here I have Fw cosine of 50, or 100 cosine of 50, if you want to write it like that. And here I have 100 newtons sine of 50. I'm just going to write 100 here. And now I write my Newton's law. So what I've done so far is we have chosen the coordinate system, we've drawn the vector diagrams, and we've resolved all the vectors. And now we're to the last step, which is applying Newton's second law. Applying Newton's second law, we say the sum of the forces in the x direction equals max, and the sum of the forces in the y direction is equal to may. F equals ma, but I make it a little more complicated because I make sure I know that this is a vector sum, that it's the net force, so I write that little summation, and then I'll also write these subscripts for x and y, because I know that Newton's second law applies in the x direction, and separately it applies in the y direction, but not together. The x and y components are completely separate from one another. So I write them as two different and distinct equations. Now, take a moment and think about what are the vector sums here. So how would you write the sum of the forces in the x direction? First, you recognize these are my forces. So how would you write that? You can go and write it down. Write the vector sum of these two vectors. It's in one dimension. So I'm going to say 100 cosine 50. I put that one first because it's positive, because remember this is positive x, minus Fs. And since this is a static problem, my acceleration is equal to 0. It's not always 0. In fact, we've had some problems where it wasn't 0, but in this case it is 0. I'll make this page bigger so y'all can see. Then the sum of the forces in the y is going to be Fn minus 100 sine of 50, and that's equal to 0. Now, once you get these equations, you return back to what you're looking for. I'm looking for mu_s. I know that Fs is equal to mu times the normal force. And so if I can find Fs and if I can find Fn, then I can find the coefficient. Do you see that you can find both Fs and you can find Fn? Yeah, Maggie?
When would it, for x, when would it not be 0? When it would have to tell you?
When it's accelerating.
So if it's telling you.
That's right, yes. Yes, when would the acceleration AX not be 0? And you could have an inclined plane where the object is moving up or down the inclined plane, and in that case, your acceleration would not be 0.
Then you just multiply by 100 for the, or 10.
By 10, yeah, the mass is 10. 100 is the weight.
Okay.
Yeah. In this case, though, it's static, so the acceleration is 0. We had another dynamic, those are called dynamic problems, where the acceleration is non-zero. Remember the elevator problem moving up and down? That was a one-dimensional problem, but it still worked out the same way. For an inclined plane, though, AY will always equal 0. Because if it's not equal to 0, it's not an inclined plane. AY is always equal to 0 because the object has to stay on the inclined plane. You follow what I'm saying? Okay, so now I know from this relationship that mu_s is Fs over Fn. And so I can solve this for Fs. It's equal to 100 cosine 50. I can solve this for Fn. It's equal to 100 sine of 50. And so my mu_s is going to be 100 cosine 50 over 100 sine of 50. The static frictional force divided by the normal force, and that's equal to point what? 0.49. All right, let's try some practice problems. Y'all give your hand. The next problem is practically the same as this problem, but just with some different numbers. So y'all can try it and see. Yeah, Maggie? No, not always. We'll look at some where you solve for different things. I'm sorry, what is it? Hold on, Maggie. I'll come back to your question. .84. Yeah, 0.84. Check, you might be in radian mode. I'll just try. Your hundreds cancel. Your question. I told you. So, see, how did we know we were solving from you? I asked you. Let's try some other questions. There are some on the next page that are very similar for you to practice on. Okay, consider this figure. What is the normal force acting on this block? Draw your coordinate system. Draw all the forces that are acting on it. Apply Newton's, resolve those forces, and then apply Newton's second law. Draw your coordinate system. Draw your vet forces. Resolve the forces. Apply Newton's second law. You're not going to get an answer that's exactly accurate because when I gave this, I'm talking about test, you're using 9.8. So your answer might be just a little bit off. All right, doing well. Most of you, all but a quarter of you or so, have the right answer. Feel free to ask your neighbor what they put. If you finish this one, just go on to the next one. All right, I'm going to stop at 2:30. 2:30. It's just 10 more seconds. Just a few more seconds. Awesome. A is right. Once you get the hang of these, you'll be able to skip some of these steps. But for now, I'm going to follow all the steps. I'm going to draw my coordinate system. I'm going to draw my forces. I have my normal force. I have some force that's holding it in place. We'll assume that that's a static frictional force. It doesn't have to be. It can be like somebody holding it in place or whatever. And then the other force is I have my weight. I know that this angle has to be 60 degrees. I can go ahead and resolve my vectors. I'll draw a separate coordinate system over here and draw my resolved vectors. I have Fn, Fs, Fw cosine 60, and Fw sine 60. That's where I've resolved my vectors. And now, you could apply Newton's second law, but since this is a static situation, I know that these two forces have to be equal and these two forces. Because the vector sum of this force and this force equals 0. That means these are equal and opposite. So my normal force, and likewise for the y direction, my normal force then is equal to Fw sine of 60, and that's 100 newtons times 0.86, or 86 newtons is what you got. Or if you do 98 times 0.86, you get 85. All right, so A is the right answer. Now let's try this one. What is the coefficient of static friction between the block and the inclined plane? All right, doing really well. I'm going to stop in about 20 seconds or so. I'll stop at 1:15. 1:15. Just guess if you're not sure. Okay, good. A is right. I think it's right. Let's just take a look. So I know that we've already found that our normal force is equal to 86. I can also find what is my static frictional force. It should equal Fw cosine 60. So my static frictional force is Fw cosine 60. That's going to equal to 100 cosine 60 are 50. And so my coefficient is going to be Fs divided by my normal force, or 50 over 86, which is 0.6. A is the right answer. Okay? Let's see. Did I tell you all how you count cows? I forget. Yeah, how do you count cows? With a calculator. Okay. Let's look at some other inclined plane problems, because I think that many of you still don't quite have it yet. Let's look at the old test in the back of your book. Let's try this number 17. Work number 17, and then we're not going to do it as a clicker question, but then ask yourself, what if the acceleration is 2 meters per second squared up the plane? We'll work that problem. So if you finish 17, then ask yourself, what must the force be if this is true, the force in the rope? But first work this problem. I got this down pretty well, I think. If you're uncertain, feel free to ask your neighbor. Any of your neighbors do have the right answer. All right, we'll do about 15 more seconds. 240. 10 seconds. Going away. Awesome, A is right. So again, same procedure we go through here. We draw our coordinate system. We draw our vectors. I'm going to draw the tension vector here. This is Ft. I have a weight. I'm just going to go and list it as 50 newtons because I know that's what it is. I know this angle is 40 degrees, and I know this is my normal force. I'm really only concerned with the x vectors because I'm looking for this tension, and so I'm going to go ahead and resolve my vectors here. So this is going to be 50 cosine of 40. And then you might just stop there because, hey, that is my tension force, 50 cosine of 40. But just to be complete, I'll go ahead and list this as 50 sine of 40. This is a 5. So sum of the forces in the x equals 50 cosine 40 minus Ft. And that's equal to 0. And then I solve for Ft. is 50 cosine 40. And that's equal, what was it, A? Was it 38? Yes. Okay, so A is the right answer. Okay? From the coordinate system, write down all the forces that I know to be acting, resolve the forces that are off the x or y axis. Usually that's just going to be the weight. Almost always that'll be the weight. Once you resolve them, apply Newton's second law. At this point, you might be able to just sort of step back and say, okay, I'm just looking for this. This is equal to this, and so I just need to find 50 cosine 40 if it's a static situation. Now let's imagine, we're not going to do it as a clicker question, but let's imagine instead of being static, it's moving at 2 meters per second squared up the inclined plane. So in this direction, how would we solve that? We're going to solve it in much the same way, except here, instead of having it equal to 0, remember it's equal to 0 because we said AX was equal to 0. We're going to write that a little bit differently. We'll say 50 cosine of 40 minus ft equals m times the acceleration. My acceleration is 2 meters per second squared up the inclined plane. So you need to be careful. It's negative. Because notice on your coordinate system, this is minus x, this is minus y. It sort of depends how it's drawn, so you have to take it case by case. Because notice if I draw my inclined plane like this, then up the inclined plane is positive x. This is positive x, this is minus x. So don't just memorize that, but just look at your coordinate system when you draw it. In this case, up the inclined plane is negative x, so my acceleration is negative 2. And then I solve for ft. So ft will equal to 50 cosine of 40, which was 38, minus the mass, which is 5 kilograms, times negative 2. And that's equal to 48 newtons. Which makes sense. It should be bigger than what we found here, because you're pulling it up the inclined plane. Okay, folks? See, I think I have some others here we can try out. Let's try this one. We'll see this. I don't know if we're going to get to the concept test problems, but let's try this one. Consider this figure. The block is stationary. Static friction is holding it up on the plane. Which of the equations is correct? So you have 4 equations. Some are correct and some are incorrect. Which ones are correct? You'll definitely have one like this. You're definitely going to have an inclined plane. You'll definitely have one like this, where I just give you the equations. Okay, doing really well. I'm going to stop in about 10 seconds. I'll stop at 140. 140. Feel free to check your answer with your neighbor. Okay, that's great. A is the right answer. We can go through. Let's look at these first and why they're wrong. Fw minus Fn equals Ma. Mainly this is wrong because, well, several reasons. First of all, the normal force is negative, but really, if we draw our coordinate system like this, my normal force is in the positive direction, so this would be Fn, and this would be Fw sine of 60. So number 2 is wrong because Fn is just not related to Fw in that same way. It's related to the y component of Fw. And then also there's no acceleration, and really for this to be right, you'd have to either put ay or put 0, because the acceleration in the y direction is 0. Let's look at 3. Fw cosine 60 equals max. Okay, that's sort of right, because Fw cosine 60 is in the positive x direction, but it's leaving out the static frictional force, which is Fs. So it left out that. In order to make this right, you would say Fw cosine 60 minus Fs, and it would be okay to have max, or you could have it equal to 0. And now these other two are correct. This one is correct, Fw cosine 60. This minus this is equal to 0. I know it's static because it says the block is stationary. And then the last one, Fw sine 60, is equal to the normal force. So these two are equal. I get that from Newton's second law. Fn minus Fw sine 60 equals to 0. And so Fn equals Fw sine 60. You'll see a problem very similar to this. I'll give you an inclined plane. I'll give you a series of equations, some correct, some incorrect. Look at the old exams. They're sample problems for every exam that we've ever had that are similar to this. Okay? You want to do another one? Yeah, William, do you have a question? 14 on this exam? Okay, number 14. Y'all want to try it? We've done one similar to this. Did you have a specific question or? Well, let's try it. Let the whole class try it, and then we'll address your question. I'm going to zoom in. Doing this number 14. This is a 1D problem, but you will have some 1D problems too, of course. I think you'll have about 4 or so. All right, we'll stop in about 10 seconds at 120. 120. 5 seconds. All right, awesome. C is right. So I have this block. It just sits on some surface. It has a mass of 1 kilogram. That means the weight is equal to 1 kilogram times 10 meters per second squared, or 10 newtons. It says that a force of 5 newtons is required to move the block. And so what is the coefficient of static friction? So what is Fs? And I also know that my normal force is up here as well. I want to know what is mu. Fs is less than or equal to mu s times the normal force. You might be a little confused because it says it needs 5 newtons to move it. But remember, you get a force right up until the maximum. That is the maximum force that's required. As soon as that force starts to move it, then kinetic friction comes into play. But this is the static frictional force. It's like the maximum that you can get. So I'm solving for mu. It's equal to Fs over Fn. Fs is equal to 5. Fn is equal to 10. So that C is the right answer. I didn't write out newtons laws, but I could say 5 minus Fs is equal to 0. Fn minus 10 is equal to 0. But as you get more and more practice, you won't have to do all those different steps. You can do them in your head. And that's all I did here because they were fairly straightforward. William, did it answer your question en route? Okay, good. Okay, we have about 12 minutes or so. Anything in particular we can, Cameron? Connor, sorry, Connor. Number 19. All right, I'm just going to work it. I'm not going to do it as a clicker question. Oh yeah, this is the one I was going to do. This is good. All right. Oh wait, no. How do you get a baby astronaut to go to sleep? You what? You rock it. Yes. You rock it. Okay. Okay, so an 8-kilogram mass is pulled across a smooth floor. Rope makes an angle with the floor. If the tension is 45 newtons, the acceleration is what? Okay, so when you see smooth here, that means no friction. So I have my coordinate system here. I can break my forces into the various components. I have 45 sine of 28. Here I have 45 cosine of 28. I skipped a step there. I have this 45 Newton vector. I just went ahead and broke it into its x and y components. And then I also have the weight, and that's it. I have the weight is 80 newtons. Now if I want to know the acceleration, it's accelerating only in the x direction, not in the y direction, because if it was accelerating in the y direction, it'd move up and down. It's accelerating only in the x direction. So I say the sum of the forces in the x equals MAX. There's only one force in the x direction. That's 45 cosine of 28. And that's equal to 8 times AX. And then you solve for AX. Is 8. Yeah, be careful. That is a common mistake that you put here for the mass. You put 80 instead of 8. But just be careful with your variables. M refers to the mass. FW refers to the weight. And while those are similar, they're different. I don't know. Yeah, if it says smooth, assume no friction. 45 divided by 8. 5. Yeah, so B is the right answer. AX. So I divide both sides by 8. This is equal to 5 meters per second squared. So B is the right answer. Any other problems y'all want to look at on this test? Number 20. Who asked that? 20 is a good one. I have two forces. This is really a vector problem. One like we've done in chapter 2. I have two forces. One is 20 newtons along the x-axis, and the other is 25 newtons along the y-axis. And then I want to know what is a third force that will give me a static situation. So, or it's not static actually, but it's moving at a constant velocity, so it's not accelerating. So the acceleration here is equal to 0. Now if I add these two vectors, I'm going to get a vector that's in this direction. So this object is going to move in this direction if those are all the forces that I have, with a certain acceleration that's given by the magnitude of this force. Right, these two vectors, 25 and the 20 newtons, will add up to give me this vector, causing it to move in this direction. So where should my opposing force be to make it not accelerate? It's going to go exactly opposite. So the opposing vector should be exactly equal but opposite to that vector. But that doesn't answer our question. I mean, it tells me the direction of where this should be, but how do I determine the magnitude of this vector? Pythagorean theorem. I say the square root of 25 squared plus 20 squared, and that'll give me the magnitude of that vector. If you don't see that, let me redraw that 25 Newton. And notice that this is a triangle now. And I want to know the length of this side. So say the square root of 20 squared plus 25 squared. Uh, 32 is what I get. C is the right answer. So it's a vector problem, but it, it's about forces. Okay? It's a third force that causes it to be, or just some third force that causes it to move with no acceleration. The test is going to consist of projectile motion. It'll have some calculations and some conceptual type problems, similar to what we've seen, and different from what we've seen, but very similar. You'll still work them the same way. And then we'll also have Newton's laws problems. You'll have some calculations, and you'll have some conceptual. For the projectile motion, let's see, you're going to have about probably 4 to 5 of these, 4 to 5 of these. For the Newton's laws, we'll break the calculations into 1D and 2D, and about 4 to 5 of each, say about 4 each. And the conceptual, you'll have about 4 to 6 of those. Does that get that up right? 5, 10, 18, 24. Yeah. Okay. That's sort of the rough way to break down of the exam. Projectile motion. You'll have some that are, just a second. You'll have some that are very similar to what we've done. You'll have some that are very similar but different, even. You have your conceptual. Make sure you look over those concept tests and the questions that we've had. Also your notes, just sort of basic knowledge about projectile motion. You'll probably have some conceptual diagrams of velocity or position versus time. And then also our Newton laws, you'll have your calculations both in 1D, like the elevator moving up and down. 1D, the force is acting only in one dimension. And then 2D, you won't have 4 calculations with 2 dimensions, but you'll have 4 questions related to 2-dimensional problems. Like the one where I put up all the equations before. And then also some calculations, like where you're calculating the normal force and the acceleration and all that there. Is that a question? No. 2014. Let's look at that because you'll probably have a question like that. In the elevator, we've worked one similar to it. Exam 2, right? This one? Elevator goes downward at constant acceleration. What is the relationship between the weight of the object and the normal force? So we can approach this in the same way that we've been doing. Bug. approach this the same way that we've been doing, where I draw my coordinate system like this. My normal force, N we call it here, is down, and my weight is up. I mean, my normal force is up, my weight is down. And I say the sum of the forces in the y direction is equal to MAY. Now, we need to recognize that our acceleration is down, so this acceleration is going to be a negative value. So I have N minus the weight equals negative MAY. I put in that negative because I know my acceleration is down. And then my normal force then is equal to the weight minus MAY. So my normal force then is less than my weight because it's equal to the weight minus this value. So our normal force is A. What's that? Is that not what I said? Okay. This value is smaller than this value. I'm sorry, I think I did say it correctly. Yeah. The normal force then is less than the weight. So the answer here is A. The normal force is less than the weight. Is that a little more clear? Okay. Listen, guys, we'll have a help session tomorrow at noon in 210. I think it's this class. It might be the other one. I'll send a message out to remind you. And then our exam is in Pelcha Auditorium, just like last week. You'll have assigned seating, but there'll be different seats. Please sit in your seat. If you're left-handed and you want a right-handed, shoot me, and I'll put you in a special seat for that. Okay? You want a special? Okay, let's try to arrange it. I don't think it's going to be a problem. I'll just just remind me. Pretty soon. Just remind me.